This meeting is being recorded.
Okay, in the previous sessions, we had seen examples 5.9 and 5.10 of your Morris Minor textbook. 5.9 was based on register reference instructions, 5.10 was based on memory reference instructions. Now, in today's session also, we'll be seeing few more examples. Let us quickly have a look at this question and let's try to solve it. The question says that show the contents in hexadecimal of registers PC, AR, DR, IR and SC of the basic computer when an ISZ indirect instruction is fetched from memory. So which instruction is to be executed? ISZ. So you have to show the contents of these registers when ISZ, what is ISZ instruction? Increment and skip if 0 instruction is fetched from the memory. And here it is also mentioned that the instruction is indirect. So indirect means the most significant bit is 1. The opcode given to you is of ISZ instruction. And let's read further. The initial content of PC is 7FF. So if I say this is my memory, this is the content of PC, 7FF. So this 7FF would be pointing to this ISZ instruction because you are said that you have to execute this instruction. Whatever is given in PC specifies the address of the instruction to be executed. So the content of PC is 7FF. At that location, you are having ISZ instruction which you are asked to execute. Let us move ahead and read the question. The content of memory at address 7FF is EA9F. Okay. So here, now see here carefully. Here they have given you that the instruction to be executed is ISZ indirect instruction. This thing can be skipped in the question. You may only be given that the content of PC is 7FF. At 7FF, you have EA9F. So from EA9F, can you decode which instruction to be executed? Is what? 1110, right? E is 14. If I write the binary of 14, it is 1110. From this, if I decode my instruction, this one indicates it is an indirect memory addressing and 110 is the code for ISZ. So even if this statement is not given, ISZ indirect instruction is to be executed, from the code itself, EA9F, you should be able to make out that the instruction to be executed is indirect ISZ. Fine? Okay. Now let us read the question further. The content of memory at address 7FF is EA9F. The content of memory at address A9F. Okay. So let us see A9F. What do you have at A9F? You have 0C35. The content of memory at address C35. You have C35 location. At that address, you have FFFF. Okay, so either you can, whenever you are reading the question, either you can draw it in the form of a memory or you can write like this: content of memory at 7FF is equal to EA9F. Then content of memory at A9F is equal to 0C35. So these are the different ways in which you extract the metadata and write it so that you can make out the question. Okay, let us move ahead. Give the answer in a table with 5 columns. Okay, so we have prepared the table 1, 2, 3, 4 and 5. One for each register and a row for each timing signal. Okay, so we know that the timing signals always start with T0. Right? So you are asked to show that what happens during each and every clock pulse, what happens during each and every timing signals. Show the contents of the registers after the positive transition of each clock pulse. Okay, so here, as we did in the previous questions, what we will do is we'll first write the initial values given to us. The initial value PC is 7FF. We are not told anything about AR, DR, IR, but yes, we know that Whenever we start executing any instruction, my SC is 0. Okay, so this was the initial data that is given to us. Now let us start executing the instruction. First of all, let me have a quick recap of what was ISZ instruction. Increment and skip if 0. What do you need to increment? You need to increment the memory word, right? Now, can I perform direct increment operation on memory? No. So what we will have to do? We will have to take this to DR. Then what happens is we increment DR, and then we restore this DR back to memory, so that now my memory has the incremented word, right? So this DR is stored to memory. Along with this, we will check the value of DR here itself. If DR is 0, I need to increment, I need to skip, increment and skip if 0. So if DR is 0, what will I do? I need to skip the next instruction. So how can the next instruction be skipped? PC equals to PC plus 1. Okay, and along with this, we will also again set back SC to 0. So this, we know that this is a memory reference instruction. So it always takes place at timing signal T4. What is the code? D6. Code for ISZ. Okay, so D6, T5, D6, T7. Sorry, 6. So these are the steps that are taking place during clock pulse T4, T5, T6 of ISZ instruction. We know that T0 and T1 are for fetch, T2 is for decode, T3 is for fetching effective address, and then T4, T5, T6, which we just wrote. Okay, so let us now start quickly with T0. What happens in T0? PC to AR, right? So whatever was my PC is transferred to AR. I'm not touching any other instruction, but yes, the sequence counter is incremented to 1 so that it can generate the next timing signal. Next, at T1, what happens? Just a minute, huh? Please hold on. Yes, sorry. Yes, so where was I? At T1, yes. In T0, what we do is, in the T0 timing signal, the content of PC is transferred to AR. Then in T1, M of AR is transferred to IR. So what is M of AR over here? AR is 7FF. So what do I have at location 7AF? EA9F. So where is it transferred to? It is transferred to AR. So EA9F is transferred to AR. And during the same clock pulse, we also increment the value of PC, right? As soon as the instruction is fetched and placed in IR, the content of PC is incremented and it will become 800. Okay, we know that during the decode phase, what would happen? Okay, first of all, let us complete this. This is T1 only. Yes, so this would remain as it is and the sequence counter would become 2. So this is T0 and T1 fetch phase is completed. Yes, so now tell me what happens in decode phase. PC would remain as it is. Okay, my 0 to 11th bit of IR is transferred to AR. So what will AR have? A9F. Okay, DR we are not touching right now. This E is decoded and we came to know that we have to execute ISZ instruction, and the instruction is an indirect memory addressing instruction. Okay, so this takes place in decoding, but we are not asked to show anything over here. So IR is as it is and sequence counter is set to 3. Now what happens in T3? PC again would remain the same. T3 is for fetching effective address. So how do we fetch the effective address? M of AR is transferred to AR. So what is an M of AR? What is an M of A9F? We have 0C3F. So here what we will get? Only the least significant 11 bits would go to AR. So AR will have, sorry, is least significant 12 bits, okay, 0 to 11 bits. So C35 will go to AR. Here also we are not using DR yet. IR would remain as it is. Sequence counter would be set to 4 so that the next timing signal is generated, T4. Again, now we know that what happens in T4, we have written it over here. M of AR to DR. So now we are fetching the actual operand. Now we are starting the ISZ instruction. So PC would remain as it is. What is in M of AR? F, 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 F. Okay, so your AR is as it is, but M of AR is transferred to DR. So what we will get in DR? F, 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 F. My IR would remain as it is. Sequence counter would become 5. Now let us see what happens in timing signal T5. DR is incremented by 1. Okay, so PC would remain as it is, AR would remain as it is, and incrementing this value would make it 0, 0, 0, 0. Okay, IR as it is, sequence counter 6. Now, in the last timing signal T6, what happens in T6? DR is transferred back to memory. Do we need to show it? No, because here we have not displayed, we are not showing the content of memory, okay? So, but yes, the updated value of DR is stored back to memory. And along with it, what we are doing is, we are checking the value of DR. If DR is 0, skip. That is, if DR is 0, increment the value of PC. So, what is the value of PC? Is the value of DR 0? Yes. So, increment the value of PC. So, it would become 801. This would remain unchanged. This would remain unchanged. This would remain unchanged, and last what we are doing is the instruction is completed. So we are again setting back the sequence counter to 0. So this is how this type of example can be solved. In this question, you were told that this is the instruction to be executed. You may be given any instruction code. Okay, here from E you decoded that the instruction to be executed is ISZ. Any other instruction can be given to you. From that you need to make out what instruction is it, and then we know the steps. What are the sequence of micro operations that takes place for execution of each and every instruction. So accordingly, you have to write the values of the content of different registers at different timing signals. I hope this question is understood to you. Okay, quickly moving to the next question. Right, this is another question given to us, 5.12. Now, in the last question, you were already told that the instruction to be executed is ISZ. But I told you that you may be given the instruction code and you need to identify which instruction it is. Okay, so here that type of question is given, that what is the instruction that will be fetched and executed. So from the given data, you need to identify what instruction is to be executed. Okay, let us quickly have a look at the question. The content of PC in the basic computer is 3AF. So PC is 3AF. All numbers are in hexadecimal. Content of AC is 7EC3. Now, content of memory at address 3AF. So, I'm writing it like this now. So, content of memory at address 3AF is 932E. Okay. The content of memory at address, content of memory at 32E, M of 32E is equal to 09AC. Content of memory at address 9AC is equal to 8B9F. Now, what is the instruction that will be fetched and executed? So, we know that, first of all, whatever is the value of PC, PC indicates the address of next instruction to be executed. So, 3AF is the address of next instruction to be executed. Okay, so this is the address. Now, what is at 3AF? We have 932E. So, which instruction would be executed? 932E instruction would be executed. Right? Now, how to identify which instruction is it? So, we know that we will be decoding this. 9. 9 is what? 1, 0, 0, 1. This indicates it is indirect. And we know that the code 001 is for add. I hope you remember the memory reference instructions. And add, load store, 1, BSA, ISZ. So here we came to know that our code is 001 and 000 add is 001. So which instruction would be executed? The answer to the A part is indirect add instruction would be executed. Okay. Now what is said? Show the binary operation that will be performed in AC when the instruction is executed. So now you know that whenever I want to perform add instruction, content of AC and DRR, content of AC and memory word. Okay, where would you get the value into DR from? From the memory word. Okay, so these two should be the operands. Now, as it is an indirect address, first of all, what we need to do is we need to find the operand. Where would the operand be located? If this is the instruction 322E, sorry, 932E, 32E address will have the effective address. Okay, and this effective address will have your operand. So what is your effective address? At 32E you will be having your effective address. So 09AC is your effective address. So what we will do is we'll go and fetch the operand from which location? 9AC. So at 9AC we have 8B9F and this is my operand. Okay, so one of the operand is 8B9F and what would be my second operand? Second operand would be this. For performing addition, accumulator and your memory word. This memory word, during the add operation, what would happen? This memory word is transferred to DR and then you perform addition of DR and AC. Okay, so but we are not asked how is the operation executed. We are just asked to tell the content of AC after this instruction is executed. Okay, so let us quickly perform addition on which two operands? 8B9F and 7EC3. Okay, so for performing addition, we can directly convert it to binary. 7 is 0111, E is 1110, C 12, 1100 and 3. 8 is 1000, B is 10, 11, 1011, this is 9 and this is F. Let us quickly add it. I hope you know addition now. I'll not be explaining it to you. E will have your 1. Okay, so what is the answer? 0, A, 6, 2. So your second part, first answer was indirect add instruction would be executed. In the second, it is said that after addition, what would be the value of your accumulator? It would be 0A62. And let us quickly have a look at the third one. What is the third part? Give the contents of registers PC, AR, DR, AC and IR in hexadecimal and the values of E and I flip-flop and the sequence counter SC in binary at the end of instruction cycle. Okay, so you are just asked to tell the values of all these registers. Okay, so PC, AR, DR, AC, IR, E, I and SC. You are asked to tell the content of this. Okay, so initially what was the value of PC? 3AF. After execution of this, as soon as the instruction is fetched, your PC would be incremented and it would become 3B0. Okay, AR. What will be stored in AR? Whatever is your instruction. your instruction is क्या था 09AC. नहीं, AR में आप जो decode phase के बाद your AR would be having 9AC. Okay. Then for performing the addition, you must have brought your second operand to DR. So this was my second operand and we stored it to DR. So what would be the value of DR? 8B9F. Then what would be the value of AC? Final answer 0A62. IR is your instruction code. What was my instruction code so that we performed indirect add? It was 932E. Okay, 932E. After performing addition, the value of E was 1. I is your indirect bit. From 9, we came to know that the value of I is 1. And after completion of the instruction, we set the sequence counter back to 0. So SC is 0. So this is how this type of question is executed. You are given some data, you yourself identified which instruction to be executed, you executed the instruction and you showed the final answer. Okay. Fine. Now we'll take one more example, one last example, small one for today. Okay. And then we'll wind up the session. Okay, let us see this one. An output program resides in memory starting from address 2300. Okay, so this is related to your IO, interrupt cycle you studied, right? So let us see that quickly. So here what is said that you have your output program and its starting address is 2300. It is executed after the computer recognizes an interrupt. Okay, when FGO becomes a 1, now we are saying that FGO is 1. FGO 1, do you remember the interrupt cycle? What happens in the interrupt cycle? The value of PC, whatever is interrupt is what we need to go and execute either the input program if FGI is 1 or output program if FGO is 1, right? So we need to go and execute the interrupt IO program and then return back to our normal flow of execution. So if I need to return to my normal flow of execution, I know that it is like a branch and save return address type of instruction. So here when an interrupt occurs, your return address is stored in at location 0. Okay, at location 1 what would we have? You will be told कि आपको jump कहाँ करना है. Where is your output program? So at location 1 what would happen? You will have an instruction called 0 bun. Here it is said that your output program starts at 2300. So at the first line in memory, you will have the instruction 0 bun 2300. It will redirect you to this location. Here, after you execute your output program, once this is executed, what we do is we set the value of IEN to 1 so that we will be making it ready to accept interrupts again. What does IEN stand for? Interrupt enable. We are enabling the interrupt so that new interrupts can be accepted. So here, for setting the value of IEN to 1, you will be right. There would be an instruction called ION. And in the last one, after this IO program completes, the last instruction would redirect you to this location, and then whatever is address given over here, you will be going back to that particular normal flow of execution. So how to do that? For that, like every function has a return statement, here also your output program would have a return statement, but this would be indirect. Why? Because we want to go to this location, and from this location we want to go to some location where we had left off our normal execution, normal instruction cycle. This was my interrupt cycle. So we'll go back to our normal instruction cycle. Okay, so what will be the last line? 1 bun, and where will it redirect me to? To location 0. Okay, so this is what is asked over here. what instruction must be placed at address 1? So what instruction would be placed at address 1? This one, 0, 1, okay, 2300. It is redirecting us towards to the address which is given over here. Okay, 2300. And what instruction must be placed at address 1 is done. What must be the last two instructions of the output program? These are the last two instructions. So before the return statement, we will first set the IEN flag to 1 through ION instruction, and the last instruction would be 1, 1, 0. Right? So whenever this type of question is asked, this is nothing but your interrupt cycle. We had studied interrupt cycle in detail, and we know what happens when an interrupt cycle occurs. So this is just the practical implementation, how it actually occurs and what are the values stored. So the at address 1 in memory, you will be redirect towards, this would be a normal branch unconditional. We don't need to come back to this location. Okay, so this is a direct, we are jumping to 2300. 2300 will have our output program, and the last two lines of the output program is this, that we will first enable the IEN flag, and then we will make an indirect jump to the location 0 where our PC is stored. Okay, so afterwards, whatever is the value of PC is suppose 22, then it will jump back to this location and execute the normal instruction cycle. So these were a few examples. In the next class, I'll be covering a very important question, 5.13 from your textbook. Okay, now today I don't have much time, so will not be moving ahead. But yes, these examples, you can try out the textual exercise examples which are given, and in the next class we'll be solving few more.